Good morning, everyone. So today I would like to bring you one example using the thrust SSC. As you have probably watched the video that I've posted for you, this is actually the world record holder for the fastest land vehicle. And I'm going to give you some information about it. So the maximum speed that it was recorded to, to be able to develop was 341 meters per second. That actually makes it a car which is faster than sound. Sound is usually about 334 meters per second. This varies a bit because it has to do with pressure, with temperature, so this speed actually changes. It's not a constant, but this car is actually faster than sound, or about the same, let's say the same order of magnitude as the speed of sound. Also, the mass of this vehicle is about 10.6 tons. And well, tons is not really useful to us, so let's write this as 10,600 kilograms. Now, the first question I could ask you is, what is the maximum kinetic energy that this vehicle could develop? So the maximum, and remember that you can pause the video, right? So you can try out yourself. Just for you to remember, kinetic energy is given by mass times velocity squared divided by 2. If I am asking about the maximum kinetic energy, then I'll just use the maximum speed. So in this case, the mass is 10,600 kilograms, and take a look, since the mass is in kilograms and the speed is in meters per second, I will expect my result to be in joules, so I will not write those down. So multiply by 341 and divide by 2. And this is squared. So if we work this out in the calculator, if I don't round the values, we would get something like 616,289,300 joules. This number has too many significant figures, and if you just write this number down in an exam, it will be wrong because you're not really sure about many of those digits. In your physics IB exam or in our school exams, you will be expected to write your results in two significant figures in most of the chapters. There will be some special cases when we're working with atoms and very small things, in which we'll keep 6 or even more significant figures, but in mechanics, 2, sometimes 3 is enough. On the cover of the exam, they tell you that on the instructions that you get from you receive your IB exam, they will explicitly tell you that you're expected to keep to a certain number of significant figures, and usually it's just 2. So I'm going to do the same thing here, and if we round this number to 2 significant figures, it would simply be 620 megajoules. So this would be the maximum kinetic energy that this vehicle may develop. Now let's open a small parenthesis here, and let's think about the unit that we got here as joules. So do you remember the equation that we had for work? Work was given as force times distance. I know this is a dot product, so there's a cosine, right? But if we're thinking about units, the maths here, if it's a dot product or a simple product, it won't matter. You're just going to multiply the units. So if we analyze the units here, on the left we have joules, and on the right it's a product of newtons, which is the measurement of force, and distance, which is the measurement of length. However, we may express force in a different way. If we remember Newton's second law, force equals mass times acceleration. And force here is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. So we can use the same units that we have here on our work calculation. So we finally get that joules could also be described in the units kilogram times, well, there's this meter here with the other meter there, so meter squared. I'll just keep each one separate, so meter squared and seconds to the -2. Those are only the units. So joule is the same thing as kilogram meter squared per second squared. And if we analyze our kinetic energy equation, that's really explicit there. The kinetic energy is given by mass times speed squared divided by 2. Speed squared is going to give us a unit of meters squared per second squared. And this mass here would just be in kilograms. So we can easily see that those two match. So even though I have not written the units here, it will be joules. So if you keep your speed in meters per second and your mass in kilograms, you will also have joules when you're calculating your kinetic energy. Just like when you're calculating work, if you keep your force in newtons and your distance in meters, you will also have joules. Now, what if I give you some more information and I tell you that the power output of this vehicle is 76 megawatts? So you could be asked, for how long was energy provided? And here it's actually very simple. If you remember, or if you check your booklet, power is change in energy over time, or work over time. In this case, we know how was the change in energy. Our vehicle was not moving, and then it's moving with that speed that I told you, which is 341 meters per second. So if it's not moving, and then it goes to that speed, we can just calculate the kinetic speed at the end, which was the maximum kinetic speed that we calculated before. So 620 megajoules divided by time. Now we don't know the time, but we know the power, so we can rearrange this equation. So before I put numbers in, let's rearrange it. So since I want to find out time, I will multiply on the left and I'll get power to the right dividing. So time will be the change of energy divided by power. The change of energy, as we calculated in the previous slide, was 620 megajoules. Remember, mega is 10 to the power of 6. The power which was delivered, the power output, was 76 megawatts. If you notice the units here, joule, that's fine. Watt is joule per second. So we're going to cross out those joules here, and that second will go to the top multiplying. And it makes sense since we're calculating some time. Also, we can cross out those megas here. It's 10 to the power 6 on top, 10 to the power 6 down below. So yeah, just get rid of them. So the time that we may sustain that power, provided we only have that amount of energy, is about 8.1 seconds. So again, this number would be 8.0 something, and I have rounded in such a way that it's now into significant figures, because this is usually the number of significant figures that we're going to keep. I'm going to repeat this throughout the whole IB course, and hopefully by the end of it, you will remember when you're supposed to keep this to two significant figures or more, especially on atomic physics, when we go into subatomic particles, when we're discussing basically properties of the nucleus and quarks, leptons, and then we'll have some more decimal places. Now, what I would like to show you now is something that we haven't discussed in class, but it's fairly simple for us to deduce now, and it's efficiency. I'll show you more ways to calculate efficiency, but basically efficiency is a rate of your useful power or energy over the total power or energy. So you can think of this as, if I give 100 joules, you could, I don't know, electrical energy, right? If I give 100 joules to a motor and it raises, let's say, some weight, and I calculate the work done to be 50 joules, well, then the efficiency is 50%. It's a half. Why? Because half of the energy that I've put in my system has not been useful. Only half has been useful. So here, for example, 50 joules would be useful and 100 joules would be the total provided energy. So my efficiency would be 0.5, which we may express as 50% as well. Now, what if I ask you what's the efficiency of this vehicle? I will have to tell you how much energy was provided to the motors, how much chemical energy was burnt. So let me give you some information here. I'm telling you that the power provided by the fuel, since we can measure how many liters of fuel have been burnt, so we have measured this to be 600 megawatts. And notice that all the values that I've been using now, they are actually true values. You can go to the research and you're going to find those values yourself. So those are reasonable. Now, if I ask you, what is the efficiency of the whole machine? So I'm asking you, how much of that power that was provided by the fuel was in fact converted into kinetic energy? Or, well, it's power output, right? So if I have a power here, I'll just compare powers. So this will be useful power over total power. And this is actually the total power. This is how much power is being given by the fuel. Our useful power is the one that we saw just now, 76 megawatts. This is the one that we actually make use of. So this is the power that was converted into kinetic energy. So this is the useful one. So if we divide the useful one, 76 megawatts by 630 megawatts, we can cross out the megas again, and our result should be around 0.12, again two significant figures, which is around 12%. So we can just say that the efficiency of this vehicle, or of this process, in this case of converting chemical energy into kinetic energy, is 12%. Efficiency is given by nu. What does that mean? Well, for every 100 joules, let's say, of chemical energy that I provide to my system, I only have 12 joules of kinetic energy. So let's say, for example, that I burn 100 joules of fuel here, enough fuel. Obviously we measure fuel in mass or volume, but let's say that I burn a certain amount of fuel which produces 100 joules. And this happens all the time inside of those engines. That's how cars move. We burn fuel, we use the energy which is released, and we make use of it. So if we extract 100 joules of energy, we will only actually make use of 12 joules. So if we apply this to this car, how fast would it get from rest if I just gave it 100 joules? Barely anything. How would you calculate that? Well, if I give 100 joules, only 12% will be useful. So we can just multiply our energy, the energy which is provided, so total, by your efficiency. So we're just changing the equation, right? We'll see that in more detail later, so you don't have to worry too much, but it's the same equation here, but you're using energy instead. So energy which is useful over energy which is, well, the total provided. So if you rearrange that equation, you can find that the energy which is useful is the product of your efficiency and the total energy. And this is also, you can also do the same thing for power, because think of energy as a rate of change power as a rate of change of energy. So if I divide both sides by a certain time, well, this will be useful power. This is still efficiency, and this is total power. All right, so we have those two relations here. And basically, you could just make this, okay, if my useful power now is only 12 joules, then you would have to make mv squared over 2 equals 12 joules. And that's going to be roughly nothing, because your car is very massive. It's in the order of tens of tons. So it's, well, it just won't move. It's too massive for that tiny amount of energy. That's not going to move it much. Just so if you want to calculate the velocity, you could, right? Because if you make mv squared over 2, which is your kinetic energy, equal to 12 joules, then we will have that mv squared will be 24 joules, and then v squared will be 24, and I'll just omit those units and assume that our speed here is in meters per second, mass is in kilograms. So this will be 24 over m, and v would be the square root of 24 over m. This is in fact, if you just write the equation without numbers, it would be your useful energy over 2 times the useful energy divided by the mass, and everything is square root. So if we do then v equals square root of 24 divided by the mass, which was 10,600 kilograms. Let's omit the units here. Okay, so that would be about 0.0476 blah 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 blah. Okay, so this is around 0.048 meters per second. So 0.048 meters per second, that's, well, 4.8 centimeters per second, right? So that's barely nothing, right? Well, at least for a car that wishes to be the fastest land vehicle, that wouldn't work, would it? Now let's get a bit crazy now, and let's assume that I take this same vehicle and I put it as a rocket, right? So I adjusted, I built some structure here to hold it as a rocket, and we want to check how high it would go if it's able to release the same amount of energy. That's cool, isn't it? So how would we do that? Well, we need to use the principle of conservation of energy. So that means that energy will never be lost. It will have to be conserved, and you just change forms of energy. So initially, you will have a lot of chemical energy inside of the engines here, ready to be burnt. When you burn that energy, the chemical energy inside of the engines will then spin some blades. It will do something here, right? In this case, it's probably just some fuel power motors. So it's going to burn the chemical energy and use that heat somehow to accelerate your car, usually by changing pressures inside of pistons. So I don't want to get too much into the detail of the mechanics itself, but basically we'll burn energy that's going to produce some kinetic energy, which will make our rocket move, and there will be a point when this rocket's going up, that, well, it has used all its energy, right? And, well, that means that all the energy provided has been dissipated. So in this case, it's doing work against gravity. So all kinetic energy is being converted into gravitational potential energy. So GP. So let's check how this works. So if I assume there are 2 times, time 1 when it's burning the fuel, so it's starting to, it's in the imminence of movement, so it hasn't started moving yet, but it's about to start moving. So let's consider this to be time equals 0. And then after a certain time, so this is point 1. And on point 2, after a certain time, my rocket has reached the highest position that it can. And then I know that this velocity is 0. Just like in the beginning, velocity was 0 as well. So in point 1, we will have chemical energy. So that's all the energy that we have. Our object is not moving, and well, if we assume that this is our frame of reference, the height is 0, then there is no gravitational potential energy. This will change with the reference, right? If I assume that my reference is in the middle of the Earth, then there is some gravitational potential energy, but potential energies, what matter about them is the difference. So what we'll have to verify here is the difference in height. So from point 1 to point 2, we know that all energy which was chemical will be converted into our gravitational potential energy. However, we didn't know the kinetic energy which was associated with that chemical energy. Remember, that chemical energy was burned, and we measured it to be, we know the velocity, right? So we know that mv squared over 2, which is the maximum. Let's put the maximum here. So this is the maximum energy that our car provided. And we're assuming now that all this energy has been converted into gravitational potential energy. So we can calculate that by mgh. And well, that's pretty simple now, because we do have a reasonable amount of unknowns. We're going to cross a few things out, and we want to calculate the height. So we know here that mass, we can cancel it out. So first thing we notice here is that the mass doesn't matter if we are calculating how high some object will get according to the energy which is provided. The mass here doesn't affect it. Now we can make the velocity here the one that we know. So we know this variable, we know gravity, we don't know the height. So let's make h our subject. And if you rearrange that equation, it would be the maximum velocity squared divided by 2 times the acceleration of gravity. If we put the values in, that's 341 meters per second squared divided by 2 times 9.8 meters per second squared. And this is about 5.9 kilometers. So this is how high that car would go if it was a rocket. That's really cool. Now I guess that's reasonable for today. Tomorrow I'm going to show you some more examples, and we should go into momentum and also discuss collisions, like elastic collisions, inelastic collisions. That's going to be fun.